Okay, so this is the second video on isomorphisms. This one is different from what we've done in class. So in the one we did in class and in the other video, we talked about how do you show two groups are isomorphic if you can stare at their tables, and basically you just set up the tables to look alike. It's a little bit trickier if you have to do it with groups that can't be represented by a table. So for example, a couple of groups that we have looked at that can't be represented by a table are real positives, or positive reals, when we look at them with multiplication, which we've already proven as a group. And another one is all real numbers under addition. So there's no way to make a table because those are infinite groups anyway, and once you list the identity element, what do you do? So, so there is a way to show that these two groups are isomorphic. These actually turn out to be isomorphic to each other. So I think, do I have the definition still here? Yeah, there it is. Okay, so there's the definition of how to prove, or definition of isomorphic groups. The goal is to come up with a one-to-one mapping. So we need a one-to-one mapping. Gosh, this pen is really killing me here. Mapping of R plus onto R such that if I pick a couple of elements from my first set, then I'm going to call that mapping phi. Then if I plug those elements into phi under their binary operator, first I combine them. So in this case, it's the binary operator of the first set. So I multiply them together. Then I'm supposed to get the same thing as phi of A plus phi of B. Okay. So now after I've plugged stuff into phi, I'm supposed to get just real numbers, not just real positives. So there's got to be some link here. So remember, it's got to go from R plus to R. And there's actually a function that, and this is regular multiplication right here, and this is regular addition right here. And there's a function you guys have learned that if you plug a couple of inputs in where you multiply them, then it's the same thing as if you plugged them in separately and added the results. And so if you stop and kind of think about different functions you've learned, basically I'm asking, like, can you think of a function, now this isn't true for sine, but where if you plugged in sine of A times B, then you get sine of A plus sine of B. Now it's not sine, but there is one like this that you've learned. Now it's not sine though, it's something else. And so if you think about it, it turns out that these are log functions. You can use log base whatever you want, but because it's shorter and my pen is not working well, I'm going to write ln instead. So ln has the property that if I have ln of xy, and remember you're only allowed to plug in positives into ln, then you get ln of x plus ln of y. The domain of ln is only positive real numbers. But the range, the stuff you get out of ln, is any real number. So if I call my phi of x ln of x, then I'm plugging in only positive real numbers. Right? My domain is only positive real numbers, but my range is all real numbers. Sorry about the pen. Okay. So And ln of x is a one-to-one function, and it passes the horizontal and the vertical line tests, that both the function and its inverse are functions. And it goes directly from all real numbers, all real positive numbers, onto all real numbers. It covers all the real numbers because this keeps going up higher and higher. And this goes all the way to negative infinity. If you think about it, if we write this, remember, phi we're defining as ln of x, then I have phi of a times b equals ln of ab, which is the same thing as ln of a plus ln of b, which equals phi of a plus phi of b. So what I have now is this, right? I've proven that I can find a function, phi, that maps r plus onto r, where if I pick a couple of elements from r plus and plug them in, right? These two elements, plug them in, then I get this fact, that this right here turns into this over here. Since I found a phi that works, which is ln, then I can say, so let me write this out. We found a suitable phi. So we've proved that the first group, r plus under multiplication, is isomorphic to r under addition. That's pretty abstract in a lot of ways, but go back and look at the one about the tables, and it's the same general idea about how this works. I can take my two items first from the first set, the r plus. I can perform my operation on them, and then I can convert it to this world using ln in this case. Or I could take my two r positive reals from the first set, convert them using ln into just regular reals, and then add them together, and I'll get the same answer. So it's like working in the first world and then converting. So working in r plus and multiplication and then converting to its real number equivalent. Or it's working with my two variables separately, converting them to the second set, right? So just any real, and then using the second set operation to combine them. It's the same exact idea as was in the tables, except now it's a little bit harder in my mind to kind of see how that works, because you don't get to just compare elements in a table. You have to compare infinite numbers of elements. So, okay, I hope that helps a little bit. One other note is sometimes you don't see how to go from r plus to r, but you might see a function that goes in reverse, and that's always okay. So let me write that down here. It's also okay. Oh my gosh, this pen. Also okay to find a function phi from r onto r plus such that if a and b are in r, then, and now I'm switching everything from r to r, I'm switching my two groups, the order of the two groups. So instead of doing multiplication here, I'm doing regular addition before I plug it into phi. And then that would turn into phi of a, and then the second operator, which is multiplication now, phi of b. And so in this case, there are functions that go this way too. You might realize that this phi is the inverse of the original phi we were talking about. So in this case, one possible function that works would be e to the x, which is actually the inverse of ln of x. So in this case, phi of x equals e to the x would work. I'm going to write the word work here. There. Okay. All right. I hope that helps a little bit. I do realize that this is a particularly kind of confusing idea. But again, that's why I would strongly recommend that you get comfortable with the table version and that definition using the tables before jumping into this version. So go back, watch that other video again, make sure you digest it okay, and then watch this one more time. Okay.